In this video, we're going to look at a couple of problems that involved impact between two particles. As a baseline, we're looking at these two blocks labeled A and B, both of them with equal mass, and we've picked 5 meters per second in the positive x direction, or to the right, for block A, and 3 meters per second in the negative x direction, or to the left, for block B. And these are the velocities just before they collide. We've defined the coefficient of restitution as 0.4, and we want to find the velocities immediately after the collision. So before we do the calculations, let's look at a simulation here. So after the impact, you can see that block A is almost motionless. It actually moves back to the left at a low velocity, and block B moves to the right after the collision at a velocity much greater than the final velocity, much greater than the magnitude of the final velocity of block A. So in block A, small magnitude of velocity and direction to the left. Block B, larger magnitude of velocity and direction to the right. So let's see if our calculations will confirm that. Well, we start out by looking at the conservation of momentum, mass times velocity of each of the two blocks added together. And so the 1 is before the collision and 2 is after the collision. And in this case, we picked equal masses, so we can delete those from the equation and put in actual numbers, positive 5 for block A and negative 3 for block B as the initial velocities, or the velocities immediately before impact. And so we can solve for the final velocity of B, but it's going to be relative to the final velocity of A. So it's two unknowns, so we need one other piece of information. And that piece of information is contained within the coefficient of restitution. The definition of the coefficient of restitution is shown here. And so we can rearrange that equation a little bit and put in both the known values and the expression for the final velocity of B that we came up with on the previous slide. And we can solve this for the final velocity of block A, and that turns out to be negative 0.6. So as the simulation showed, after the collision, block A moves back to the left at a relatively low velocity. Using that value and plugging into the expression we have for the final velocity of block B, we calculate that the final velocity of block B is positive, so it is to the right, and has a magnitude of 2.6 meters per second. So approximately the same magnitude of velocity that it was moving with to the left before collision. After the collision, it moves back to the right. Now we might ask, could we have used conservation of energy as one of our equations here? And to check that out, let's look at the energy before and after the collision. Before the collision, we have this expression for kinetic energy. There is no potential energy here. And so putting in our known values before the collision, we see that the total kinetic energy before the collision was 4,250 joules. Plugging in the masses and the velocities that we calculated after collision, we see that the kinetic energy after the collision is only 890 joules. So we see that 79% of the kinetic energy before the collision was lost during the collision. Now, we could look at some variations of this problem, but to do so, rather than go through step through the calculations for each one, let's set that up on a spreadsheet. So let's work the equations out symbolically here. Here's the conservation of momentum. And again, do a little bit of algebra here, manipulating and get that into an equation for the final velocity of B, and the equation for the coefficient of restitution. Again, rearrange that a little bit, put in the expression from the previous slide, and again do a little bit of algebra that I'm skipping over pretty quickly, but I want to isolate the final velocity of A. And so that comes out to the expression that's shown here. So you can see, obviously, it's going to be a function of the initial velocities, a function of the mass ratios, and a function of the coefficient of restitution. And so we have an expression on the previous slide for the final velocity of block B, and we can calculate the energies before and after and look at the percent energy loss. So there's the calculations shown in a spreadsheet, and let's open up the spreadsheet and maybe do a few variations here. So here's the baseline. Well, actually not the baseline case. I need to change this one back to 250. Okay, so there's the best baseline case showing the final velocities that we calculated right here and the energy loss that we calculated. But let's look at some variations. The coefficient of restitution we know can vary between 0 and 1. If we put in a value of 1, we can see that the final velocities are just switched from what the initial velocities are. That is, the velocity of A after the collision is the same as the velocity of B was before the collision, and vice versa. You can also see that there's no energy loss. At the other extreme, we can set this to 0, and we can see that the velocities match after the collision, and that indeed most of the energy gets lost here, a total of 94%. Let's set it back to 0.4, which was our baseline value. And what if instead of the two coming together, approaching each other in different directions with velocities, what if the velocities are in the same direction so that B is overtaking A? Well, you can see in this case the energy loss is very low, only 5%. And finally, one more case, let's set this equal to 0, but let's make the two of them coming together at the same speed. So one moving to the left, one moving to the right. And you can see in this case, the final velocities are both equal to 0, and so 100% of the energy is lost. Let's look at those cases on our SolidWorks simulations. So this was the case where we took the baseline velocities and set the coefficient of restitution equal to 1. And see, after the collision, the blocks are moving at the speed of the other block before the collision. Let's look at that same case, same velocities, with the coefficient of restitution equal to 0. With the coefficient of restitution of 0, the blocks will stick together and move together after the collision. In this next one, block A is going to be moving at 5 and block B is going to be moving at 3 meters per second, both of them to the right. And so we saw there wasn't much energy loss, and you can kind of see why. The collision is not is kind of a gentle collision here when one of them is overtaking the other one. And finally, the last case we looked at, the two of them are coming together at a velocity of 5 meters per second each, and if the coefficient of restitution is 0, then they'll simply come to a stop. Now we could also look at the case where, what if the masses are not equal to each other? But before we do that, actually I want to go back and look at one more slide here. Actually a couple of them. The special cases, one of them where the coefficient of restitution was 0, results very easily. You can determine that the two final velocities are going to be identical, and we saw that in a couple of cases. And the other case, without working through the algebra, but we saw that when coefficient of restitution is equal to 1, that energy is conserved. And so we can make a graph using our calculations here, and what we see is that if we plot the energy lost versus the velocity ratio, so on the left side would be the velocity ratio of -1, in other words, where the two of them are coming together, coming towards each other at the same magnitude of velocity. And so 100% energy loss occurred when that happened and when the coefficient of restitution was equal to 0. And you can see across the bottom, the coefficient of restitution being equal to 1, that there's never any energy loss regardless of the velocity ratio. As we approach the right side of the graph, well, that's a velocity ratio of 1. Well, if we have a velocity ratio of 1, there's not going to be a collision. So as we approach that, though, like the glancing blow that we saw when one of them was 5 and one of them was 3. The energy loss is very low and it approaches zero as the velocities approach each other. Now, as we said, one of the other things we could look at would be looking at masses that are not equal to each other. So in the first case, let's go back to our baseline case. 5 and minus 3 are our initial velocities, and 0.4 is the coefficient of restitution. So you can see in this case the energy loss is significantly less than it was for the baseline where the two masses were the same. And you can also see the velocity of B is going to be bouncing off at a relatively high speed. Another one we can look at where the two of them are coming together at the same speed and the coefficient of restitution is equal to 0. Well, you can see in this case the final velocities are equal, but we don't have the 100% energy loss that we saw in the baseline case where the two were the same mass. Now, of course, there is going to be a case where 100% of the energy would be lost, but to do that, what we would have to figure out is what is the if the energy is totally lost, then the final two velocities are both going to be equal to 0, so the final momentum is also going to be equal to 0. That means that the initial momentum must be 0 as well. And so if we set this one, the velocity of A, as being half the velocity of B, but in opposite directions, that says that our initial momentum is 0, therefore the final momentum is going to be 0, and therefore 100% of the energy is going to be lost. And so we can look at those scenarios here, starting out again with the baseline case as far as the velocities go and a coefficient of restitution of 0.4. You can see that the lighter block bounces off the heavier block and picks up a lot of velocity there. This will be the case where they approach each other at 5 meters per second with a coefficient restitution of 0. So the two do stick together, but because the block A is carrying in a greater momentum, it's going to push both of those to the right after the collision. And finally, moving over to this last one here. Finally, we get a 100% energy loss when the velocities are such that, relative to the masses here, such that the initial momentum is 0, therefore your final momentum will be 0 as well. So, to summarize, you can solve the impact problems using the principle of conservation of momentum, and you also need the definition of the coefficient of restitution. And with those two pieces of information, or those two equations, you can solve for the two unknowns, which would be the two final velocities. Your limitations of the coefficient of restitution, the upper limit is 1, which is a perfectly elastic collision, and in that case, conservation of energy is also can also be applied. If the coefficient of restitution is 0, we call that a perfectly plastic collision. You can think of the two blocks as sticking together at that point, and the two will move with the same velocity after the collision. And energy loss depends not only on the value of the coefficient of restitution, it also depends on the relative masses and of course the relative velocities before the collision. Now, kind of a preview for what we're going to look at next time. Let's take a look at the case where we have, actually before we do that, let me go back to the case where we just have the two. And we want to look at a special case where the velocity of block A is given. In this case, it's going to be 5 meters per second, and block 2 is has an initial velocity equal to 0, and the coefficient of restitution is equal to 1. In that case, after the collision, block A will stop and block B will move along with the same velocity that block A came in with. And now let's go back to the one we I just started to look at. When we have a line of blocks like this, what's going to happen? Well, we can think of it as being a sequence of the collisions like we just looked at. And so what's going to happen is the one on the end is going to fly off with the same velocity as the one that did the impacting at the beginning. And so we're going to use that next time to take a look at what's sometimes called an executive toy, the Newton's cradle. And you've probably all seen that work before, but looking at that a little more in depth will help us understand impact even a little further.